Hello everyone, in this video we're going to be talking about sums. So, what is a sum? Well, a sum is often written in what's called sigma notation. So this thing that kind of looks like an E is the capital Greek letter sigma. And the general form is the sum from I equals m to n of a sub I. I is the index, and m is our starting point. So the thing on the bottom is where we start, and the thing on the top is where we end. So n is our ending point. And that thing on the inside, what's called the summand, we can think of it as a function in terms of I. So we can think of a sub I as a function f of I. So how do we interpret this? So we can think of the sum from m to n of some function a sub I as am plus 1 plus am plus 2 all the way up to am plus n. Remember that these are functions in terms of I. So we can think of this as like f of m plus f of m plus 1 plus f of m plus 2 and so on. Now, let's look at an example, just using this, and breaking it up from sigma notation, unpacking that, and putting it into some sort of sum that we can deal with. So, we'll take a look at the sum from 2 to 7 of I squared. So, what's our starting point? We start at 2, we end at 7, because that's the one on top. And our function, we can think of this as f of I or f of x. Either way, it's going to be the thing that we put in, we're just going to square it. So this sum is 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. And by squaring it all out and simplifying, combining the numbers, we get 139. So for our next example, let's look at the sum from 0 to 4 of 2 to the I. So for all these problems, we look at our starting point, we look at our ending point, and we think of our function. So as we can see, the bottom is 0, the top is 4, and our function on the inside is just f of x is equal to 2 to the x. So we're just going to write it out. It's going to be 2 to the 0 plus 2 to the first plus 2 to the second and so on. And then we can just evaluate that. So 1 plus 2 plus 4 plus 8 plus 16. And that's going to give us 31. 2 plus 8 is 10. 1 plus 4 is 5. That gives us 15. 15 plus 16 is 31. All right, so now we know how to unpack stuff. But what if we have something that we want to pack up instead? Because it turns out that in a lot of cases, sums are easier to work with than a string of things being added together. So let's take a look at an example of 2 cubed plus 3 cubed all the way up to 6 cubed. So we want to write this as a sum. So we know it's going to be the sum of something. We're going to have to start somewhere, we're going to have to end somewhere, and we're going to have a function in terms of I. Now, I often find it easier to start at the function. So what do we notice? We notice everything's being raised to the third power, and we're starting at 2, and we're just incrementing by 1 until we get to 6. So f of x is going to be x cubed, because no matter what we change our I to be, we're always going to be cubing it. We start at 2, and we end at 6. So we can just fill in everything in our sum now. So I equals 2 to 6 of f of I, but f of I is just I cubed, so we can just put that function right in there. Okay, for our next example, we're going to start at a defined point, but our ending point is going to be something kind of ambiguous, and we're going to call it n. So the problem here is to write 2 to the 4th plus 2 to the 5th plus so on to 2 to the nth in what's called sigma notation. So sigma notation and writing it as that sum are the same thing. So we want to write this big string of things being added together as one nice compact package with a sigma in it. So as usual, we're going to need to identify our starting point, our ending point, and our function. And even though the function's written last, I like to find that first because it kind of tells us everything else that goes on in the sum. So to identify our function, let's notice what's the same and what's changing. Okay, if we look at the sum, we can see that the 2's are always the same, and it's the 4, 5, 6 that are always changing. So f of x is going to be 2 to the x. Now with that in mind, we notice that we're starting at 4 and we're ending at n. And now we have everything we need to write our sum, which is going to be from 4 to n of 2 to the I. All right, next, now that we have the basics of what a sum is, let's talk about some properties that are going to make our lives a lot easier when we're evaluating these things. So the first one is the sum from I equals 1 to n of 1. Now if we were to write this out, it would be 1 plus 1 plus 1 plus 1 n many times. And we know that since multiplication is just repeated addition, this is the same thing as n times 1, which is just n. So this guy is property 1, which says the sum from 1 to n of 1 is just n. We could start at 0, but then we'd have to change our top index to n minus 1. As long as we're adding something to itself n many times, it's going to be n. So property 2, we're looking at the sum of c times a sub I as I goes from 1 to n. We could replace this with m as well. And it won't really change anything. Where c is any number, so it could be like a 2, a 7, it can be anything. So property 2 says we can take that constant and we can pull it outside of the sum. So we can rewrite this as c times the sum from m to n of a sub I. Okay, and why is that? Well, if we were to take CAI and write it all out, we get CAM plus CA sub m plus 1 plus CA sub m plus 2 plus C a sub m plus 3 and so on, all the way to CA sub n. Notice that the C's have a common the sum, when we write it out, has a common factor of this constant in it. So we can just pull it out. And we get C times AM plus AM plus 1 plus AM plus 2 all the way up to AN. And we know that AM plus 1 all the way up to AN is just the sum from m to n of a sub I. So it's c times the sum of a sub I. Now, the next property combines 1 and 2. Okay, so property 3 says that the sum from 1 to n, or 0 to n, this should be a 1 to n, of c is going to be cn. If we were actually summing it from 0 to n, it'd be c times n plus 1. But the idea here is that the sum of c is the sum of c times 1. So by using property 2, we can pull the c out, and we get the sum of 1, which we know is n. Okay, so property 4 now, it tells us how to deal with sums and differences of these sums. So in general, the sum of a sub I plus or minus b sub I is the sum of a sub I plus or minus the sum of b sub I. And that comes down to the fact that a sub I and b sub I are just functions where you put in a number and you get out a number. And we know that numbers are associative and commutative, at least real numbers are, so we can rearrange them so we have all of our a sub i's together and all of our b sub i's together, and we get that, at least for the addition. For the subtraction, what we're going to do is something a little different. So the thing to notice is if we have a difference of two things, a sub I minus b sub I is the same thing as a sub I plus negative b sub I, which is also just a function in terms of I. So what we can do is we can call negative b sub I some other function, c sub I, and identify c sub I with negative b sub I. Now we have a sum of two things. We can split that sum apart just as we did in the first half of this explanation, and then bring it back, substitute the negative bi in for ci, and then notice that negative b sub I is the same as negative 1 times b sub I. So we can pull that negative 1 out, and a number plus a negative 1 times something is going to be the sum of a sub I minus the sum of b sub I. So now that we've looked at all the properties of these different things and how we can work with sums, let's actually do an example where we work through the sum. So we're going to be looking at the sum from 3 to 16 of some function. And that function is going to be 3i plus 7. And we're not actually going to evaluate what the function is. We're just going to simplify it and write it in terms of two sums in simplest possible form. So since it's addition, we can split it up and make it the sum of 3i plus the sum of 7. 3 and 7 are just constants, so we can pull them out. And we'll get 3 times the sum of I plus 7 times the sum of 1. And that 3 times the sum of I plus 7 times the sum of 1 is going to be our simplification. It's in simplest possible form without actually evaluating the sums. So now that we have an example, we know how to work with these sums kind of and split it up and writing it into two different sums. Let's look at some useful formulas that are actually going to help us evaluate these sums. So the first one is the sum from 1 to n of 1 is just going to be n. We've already seen that, but let's just write it down. The second formula is going to be the sum from 1 to n of I, and that's going to be n times n plus 1 over 2. I'm going to show you guys why that works, but you don't actually need to know the details as to why it works. Just know this is what it is. In similar ways, you can prove parts C and D, but C says that the sum of I squared from 1 to n is n times n plus 1 times 2n plus 1 all over 6. And the last one, we're just going to look at I cubed as we sum up from 1 to n. and that's going to be n squared times n plus 1 squared all over 4. If you stare at it for a little bit, you'll notice that it's related to the solution in B. And in fact, it's the square of it. So this is both n times n plus 1 over 2 all squared, but it's also the sum from 1 to n of I all squared. And our last property, it's just a generalization of part A, which says the sum from 1 to n of any constant is that constant times n. So for instance, why does property B work? And if you're not interested, you don't plan on going further in math, you can skip this section. But the idea is the principle of mathematical induction. So the idea of induction is we start with what's called a base case. And normally that's 1, but we can start at any number here. And we start with a base case. We show that it works for our first one. And then we pick an arbitrary number. I think I call it k. And if we show that if it works for 1, and then if we assume it works for some arbitrary number, then it works for the next one. We can think of this kind of like dominoes falling. So the base case is knocking down the first domino, and then what's called the inductive step is essentially saying that if one domino falls, then it's going to knock the next one down. Then it works for everything bigger than the thing we started with. So in this case, we're going to start at 1, and we're going to show it works for every natural number. So we're just going to go through the example, the summing 1 plus 2 plus 3 plus 4 all the way up to n is going to give us actually the thing that we want, n times n plus 1 over 2. So our base case is just n equals 1. We have to start somewhere and we have to work with something. So we're actually just going to work with n because that's the only thing that we can actually control here. So the sum from 1 to 1 of something is just 1. Just how the sum from 3 to 3 of I would be 3. But 1 is 1/2, which is 1 times 2 over 2. And we want to get it into that n times n plus 1 over 2 form. So we write it as 1 times 1 plus 1 over 2. So it works for the first case. Next, we're going to show that if one domino gets knocked down, it's going to knock the other one down. So we assume that the sum from 1 to k is k times k plus 1 over 2. And we're going to look at the next one in the set, or in the series. So the sum from 1 to k plus 1 of I is 1 to k of I plus the k plus first term. So it's the sum from 1 to k plus k plus 1. Now, by our assumption, we assumed that adding 1 to k of I is k times k plus 1 over 2, right? We're assuming that it works for what we're starting with. So we're just going to take that sum, unpack it into this formula, and we're going to add k plus 1. And then we're just going to do some algebraic simplifications and manipulations, and we're going to get into that form that we want. So since the first one works, and since if it works for any number, it works for the next one, it works for every natural number. And that's the end of this optional section. So now we're going to look at a solid concrete example as to what to use here. We're going to look at the sum of I times 4i squared minus 3. Notice that it's not equal to I times 4i squared minus 3. Because I is the thing that's being added up. So we can't pull it outside, right? That'd be like saying f of x is sine of pi x. We can't pull the x out because the sine is working on it. So step 1, we're just going to distribute that I into it. And we get 4i cubed minus 3i, just by distributing. Next, we have a difference of two things. So we're going to split it up. And we're going to get the sum of 4i cubed minus the sum of 3i. Next, we notice that we have 4 and 3 as constants. So we can just pull them out. And we'll get 4 times the sum of I cubed minus 3 times the sum of I. After that, we are going to just use our formulas to evaluate what the sum of I cubed is and what the sum of I is. So we're going to get 4 times n squared times n plus 1 squared all over 4 minus 3 times the sum of n times n plus 1 all over 2. And our final step is to just use algebra and simplify this to get it into its simplest possible form, which is n times n plus 1 times 2n cubed plus 2n minus 3 all over 2. So far, we haven't done anything using calculus, right? We've just taken sums apart, we've done algebra, we haven't really done any calculus. But we know that calculus is just the study of limits. So we're going to have to throw a limit in here somewhere, otherwise we wouldn't be in calculus. We'd be in pre-calc or algebra or something. So what are we going to take the limit of? Well, our options are pretty limited. Our index is going to just change based on our function. Our starting point, we could take the limit of it. It's kind of a mess. But the top is the thing that we're actually going to take the limit of. So that n is the thing we're going to take the limit. And we're going to take the limit as n goes to infinity. Now, I want you guys to pause the video just for a second and think about why taking the limit as n goes to infinity is the only limit that makes sense. So the reason is, if we just take the limit as n goes to any number, we just end up with a finite sum, and we wouldn't need calculus. So infinity is the only thing that we can actually take the limit of that makes sense, and we would need calculus for. Now let's take a look at an example here. So for this example, we're going to take the limit as n goes to infinity. We're just going to take the limit of the sum from 1 to n of 3 over n times the quantity of I over n squared plus 1. Okay? So just like taking limits in the beginning of Calc 1 when we were learning to take limits, we're going to simplify it. And the first thing we're going to notice is that 3 over n is constant in the sum. Why is it constant in the sum? Well, it's because I is the only thing that's changing in our sum. This 3 over n doesn't change as I changes. It's still going to be 3 over n. So we say that the sum only depends on I. So since it's a constant, we can pull it out. And we're just going to look at that I over n squared plus 1. So this guy is going to become the limit of 3 over n times the sum of I squared over n squared plus 1. And now we're just going to use all of our properties that we've been working with so far to simplify this sum as much as possible. And then after it's as simple as it can possibly be, we'll take the limit. All right, now that we're at the end of our simplification process, we'll notice that we have a polynomial over another polynomial, and they have the same power. So we can just take the ratio of their coefficients, and we're just going to get 1. And the limit of 3 is just 3. So at the end of this whole process, we get that this nasty sum that took forever is just 4. All right, and that's the last example we're going to do, but I do want to make a note on some notation here. So if we look at this like the limit of the sum, it's really unwieldy, and writing sums is already kind of complex and kind of a pain. So the more we can simplify this, the better. So what we're going to do is we're going to take that limit as n goes to infinity, and we're just going to throw it up top. So we can rewrite this instead of the limit from 1 to n of a sub I, we can just write it as the limit as I goes from 1 to infinity of a sub I. And that's just a notational thing. It might be something that you see in future exercises. I might use it in a future video, but that's pretty much it. So to recap everything that we've done today, we've talked about what a sum is, we've talked about properties, we've talked about how to simplify them, and we've talked about how to do limits and take limits with them. So if you have any questions, feel free to leave them in the comments. If you're one of my students, feel free to email me, and I'll see you in the next video where we'll be talking about areas and how to actually apply sums to stuff that we're going to be dealing with further in calculus, and how it relates to something that we'll see eventually called the definite integral.